well, the end goal is a 3D printer that astronauts would be able to just take with them on their space travels, to be able to print whatever spare part they need and tool that they lost. Because if you lose something in space, it's not like losing it in the backyard. Yes, you have to.
For sure, yeah.
Welcome everybody to a new episode of Your Friendly Physicist and Other Nerds, your science podcast where scientists speak about their fantastic research, their visions, dreams, challenges, and their daily life in the fabulous world of science. My name is Lucas, I'm your friendly physicist, and today we will go into space with Mélanie Clozel and her 3D printer. Just a short disclaimer before we start. This episode was the very first episode I recorded, and back then I only had one microphone, and that's why the audio quality might be a bit noisy. I'm very sorry for that, but nevertheless I wish you a lot of fun with this episode, so let's start.
So I'm really happy that you are here. Let me shortly introduce you properly. So you finished engineering school in France, and after that you studied mechanical engineering at the Technical University of Kaiserslautern in Germany, as well as the university in Breslau. No, that was not correct.
The mechanical engineering was in France at the INSA, and then the Masters in Material Science was in Kaiserslautern.
Okay.
So you were close,
Shame on me. But it's true that you studied in Kaiserslautern as well as in Poland, in Breslau, for your masters.
Yes.
Okay, and then you continued to work in a nuclear research center in Warsaw, also in Poland, for 2 years, and now you're back in Germany at the Material Physics and Space Institute at the German Aerospace Center in Cologne, and this is also the place where we are right now. So we are colleagues. I'm also working here. We have almost next door offices, and when I first heard about your research topic, I knew for sure that I have to do an interview with you. So you literally were the first name on my guest list because first I think you're really a great scientist, and I also think that you have a super exciting topic. Welcome. I'm really glad that you are here.
Well, thanks. It's nice to have the opportunity, I guess, even if it is a little stressful.
It always is. This is, I think, the default state of a scientist. I have a very first question. After all this time, your studies in France, in Poland, in Germany, you are still in science. You're still in the lab preparing samples. You're still doing measurements. You're still preparing measurements and everything. Why are you a scientist? Why are you still a scientist?
The reason I became a scientist was more out of chance, because during my studies I was studying to become a mechanical engineer and as such more into leading projects or working in car companies and things like that. But in Germany I had more of the opportunity over the masters to do more kind of research, and that was quite fun. And I also really liked the excuse to do lots of literature research because you have to do it, and I like reading and just always being able to learn something, which is something you get in studies. You're constantly learning stuff, which is really nice. But once you start working, like I did a 6-month internship in Stuttgart in a material science lab, but it wasn't really science, it was just testing material all day. And basically after the first month I had done all the different things, learned all the different techniques, and I would just repeat them every time, and it just got really boring, I guess. So then I thought, research sounds nice, and by chance I got this job in Poland, and I enjoyed it very much, and the colleagues are really nice as well, so that has to go together. You have to have a nice work and nice colleagues.
That's true, that's true.
So that's why I stayed in science at that point, and when I came back to Germany I didn't particularly have a plan for anything, but I found this job offer here, and it's like research again, but the topic just sounded like really great, so I thought, okay, why not?
That's so cool. I'm feeling it because I also like to learn, and I think that this is really something that academia is very good at, that you gather around people who are eager to learn new things and are curious about knowing stuff, knowing new stuff all the time. But is there anything particular why you joined then the DLR and the Institute of Material Physics in Space?
No, that was just pure chance. Looking at different job offers or PhD offers and finding this. And if you find 3D printing of metals in space, you're like, yeah, sure, I'm going to do that. That sounds great.
Yeah, that's a really good keyword because I think we teased enough that the topic is super exciting. So let's dig right into it. What is your research about? So can you summarize it in a few sentences?
The project is about developing a 3D printer that would be able to print several metals, particularly special metals in this case, with cool properties in microgravity or different gravities even. So our device would then be able to work in space, but also on planets with different gravities. That's kind of the point.
So 3D printing in microgravity, how does this work? Or is there anything you have to especially keep in mind when you develop a printer for space or for microgravity compared to a regular printer on Earth?
Our printer is based on laser powder bed fusion, which is kind of a long word, just meaning that you use powder and you use a laser to melt the powder where you want your sample to be, isn't the part. So there are different aspects to this. First, you have to develop a technology that actually is capable of handling the powders in space, so keeping it stable so it just doesn't float all around as you would expect it to do without gravity. And second, you have to optimize the printing parameters, because there are tons of parameters you have to be careful of. So laser power, laser speed, powder layer thickness, the hatching distance, which is basically the distance between, when you do two lines with the laser, how far do you want them to be from each other so that they don't kind of overly impact each other and steal the material from one side. Anyway, whether or not we want to preheat the plate we're building on, because that also affects the cooling rate and so the material properties in the end. So it's a bit, there's a lot of tricky stuff to think about.
I see. The sounds overly complicated at first sight or first hearing. So maybe let's start with the big questions. Why is it important? So what do you do with the 3D printing stuff in space?
Well, the end goal is a 3D printer that astronauts would be able to just take with them on their space travels, to be able to print whatever spare part they need and tool that they lost, because if you lose something in space, it's not like losing it in the backyard. Yes, you have to
for sure, yeah.
Definitely be in trouble. So it's more about that, because without this, every time we have to send extra missions from Earth just to give them the spare parts, and that costs enormous amounts of money. It takes time. Often it doesn't work at all, and so you have to repeat it. And it would be so much easier if astronauts could just print on their spaceship or space station. Another side of this is that if we develop something that can print with powders in different gravities, is that we can then print with different materials that we find on site on new planets we discover, which would be really cool.
Very smart, for sure. Being able to print your own, I guess it would be then tools like a screwdriver or a what's it called?
Even cutting tools.
Stuff. Mm-hmm. Another question that comes to my mind is how big is this printer? So what are the dimensions of the printer, and what are the dimensions of the object it can print by now? And is this already finished, or is there still I guess there is room for improvement? But what's the current state?
There's a lot of room for improvement. Firstly, because Mars M, our printer, is Mars M for Malfoys.
So Mars M is the name of the printer?
Yes, because Mars is metal-based additive manufacturing for research in space.
Or it has nothing to do with the planet Mars?
No, it just sounds cool.
Okay.
That was
fits
the point.
perfectly to the space topic.
And it means that all our logos have Mars in it. Anyway.
Yeah, nice.
So yes, Mars M is built to fit on the Morpheus rocket, the DLR Morpheus sounding rocket, and so as such it has to have a given size and can't go above certain dimensions, right? So it's about, I think, 70 centimeters in diameter, and a bit more, maybe 80 in height or something like that.
Okay.
I'll have to look more into.
What's the weight? So how heavy is it?
About 70 kilos, I think.
70, okay.
Most of that is really the outside hull, because basically you don't just fit all these experiments into the rocket, they are part of the rocket on the outside, so that adds a lot of the weight. So that's the size of the printer itself, and the area we actually print in is on these little plates that are about 45 times 45 millimeters. Millimeters, yeah.
Okay, right. It's a starting point.
Exactly, but it's because of the limitations of Morpheus. Because we're making the Mars X, which would be for the in situ in the synchrotron beam on Earth, but then the plan after that is Mars S for satellite, and that would be able to print then larger parts and several at the same time, which would be pretty awesome.
Okay. So you mentioned quite often Morpheus, the sounding rocket. I think it's time to introduce that, because I think this is the vehicle you're using to create microgravity conditions. How does that work?
You shoot a rocket that goes about, what was it, over to 200 kilometers.
So it's in space.
It's in space, yeah. And so you get 6 minutes approximately of microgravity.
6 minutes while it is in space, and then it falls down, and then the parachute opens and it touches the ground.
The point is to recover the experiments. So.
Yeah. Maybe a short summary. So you have a portable 3D printer. You place it on a rocket, this Morpheus rocket, and then you just send it to space, and then you have several minutes of microgravity conditions, and in these minutes you try to print your material. And this is like automated or controlled remotely from Earth, or is it fully automated?
It can just function automatically, because the device recognizes when it is in microgravity, and it also gets a confirmation from the rocket's intelligence, let's say, I don't know how to call it. And so the device knows, okay, time to start printing. It has an on-boot code, a code that it knows it should print. But as observers, interactors from Earth, we can also just, if we see that it's not doing what it should, we can just stop it, and or stop the laser, or just let it do its thing without the laser on, and things like that.
And then you can restart it, like while it's flying, you can stop it and restart it, or recalibrating, or is it?
There's not enough time for that. That's the problem, especially for our whole process. Adding the powder layer to the plate is actually what takes the most time in the end, because you need to give enough time to the powder to actually flow onto the plate, because the whole method of keeping the powder on the plate is through a gas flow, because the plate we build on is porous, and so we have this gas flow going through the plate that keeps the powder held onto the plate.
So you have like a powder bed that is like sucked through this plate.
Exactly.
It's like a giant vacuum cleaner or something.
Yeah.
Gas circulation.
Yeah.
And out of this powder bed, you then laser print or laser melt your object.
Yeah, every time we add a bit more powder, and we laser where the part should be on that layer, and then next layer we laser the powder where it should be. So it just holds together.
So if constantly like a new layer, then the printing process, new layer, then the printing. Okay, I see. Okay, and after this like 6 minutes of microgravity, your experiment is done, basically.
Yes.
It has to be done, because then you don't have microgravity anymore.
Exactly.
And then you have a fully printed object. I think you printed this DLR logo. I saw it. You showed it once to me.
Yes.
But this is then printed within 6 minutes.
Yes.
That's quite impressive.
Usually we have enough time for about 8 layers. So that's 0.8 millimeters in thickness. 0.8 millimeters in thickness in total.
Okay.
It doesn't sound so impressive.
But it's not. too small, I think. I mean, I have just a regular 3D printer at home, which just prints like plastics and has a thickness of like 10 micrometer, 20 micrometer, which is 0.2 millimeters.
Mm.
No, 200 micrometers, 0.2 millimeters.
Yeah.
So it's thicker than a regular 3D printer. Okay. Where do you? I assume you don't launch your rocket from your backyard. So where does this happen?
This is all done from Kiruna, as an S-range in Kiruna in Sweden.
In Sweden.
Yeah.
Northern Sweden, I think.
North of the polar circle, so yeah.
Okay. I think it's beneficial that there's not too much like traffic or cities or people.
You'd be surprised because every time where the rocket lands is in the Sami territory where they keep their reindeer. And so every time we have to warn them first and ask them is it okay if we do it now? Because sometimes they have this huge gathering where they exchange sale and everything, these reindeers, and then you have to just pause the campaign for 2 days.
Okay. How many are they?
I have no idea. Not that many, but they go over huge territories because the area is just too cold and icy for anything else, basically.
So that means every time you have like a countdown or a rocket, you first ask them, like you call them, or do you?
Yeah, the Swedish people in S-range, they just call them, ask, okay, how is it going? You know.
Yeah, and then they say yes or no, and if yes, then you can continue with your countdown.
Exactly.
Okay, nice. So you were there in Sweden. How long does it take to prepare such a rocket before it can take off?
Well, the first time I went, the whole campaign took us 18 days. And the second time I went, it was the second half of a double campaign where I hadn't gone to the first half, so everything was already in place and set up. That was a lot easier, so it only took us 15 days.
Okay, but several days or
yes,
like 2 weeks plus.
Usually yes, because obviously there's all the work on the rocket, putting it together and preparing motors, whatever. But on our scientific side, obviously you test and retest and retest your device to make sure that it will be fine. And still, there's always things popping up that you then have to fix, things that have been used X number of times, and that they decided that they're not going to do it anymore.
I know that feeling. Testing, retest. You cannot test enough.
Yes.
So Mars is not the only experiment on this rocket.
No.
So there are several. Like how many experiments are there?
Last time there were 4 because there were Mars, there was SOMEX that studies the impact of gravity on granular material and colloidal suspension.
Okay, sounds also maybe you have a contact for next episode.
Exactly. Then Graviplex, which is pretty cool. That you should. Which is studying the impact of gravity on cell polarity and cancer development by studying basic cells, what they call animals, the trichoplax adherents, and how they move around and grow without gravity.
Okay.
That's from the Luftmedizin.
Oh, nice. It's also here, right, on the campus?
Yeah, it's the building right next to us. And the guy who takes care of this is really nice, so
cool.
Feel free, that's probably an option.
For sure, we'll check it out,
And then the last experiment was Grasha, which is studying the pressure dependence of the sound of speed in low pressure environments. So it's very specific.
Okay.
But yeah, they all sound cool.
So 4 experiments, and then they are like stacked on top of each other.
Yes.
Within this rocket.
Yeah.
Okay. What are the dimensions of this rocket? So you said like your printer is in diameter, that's 57 or something. You said.
I think it's 70, but
or
I'm
70?
yeah.
So that's also the diameter of the rocket.
Yes.
Okay. And what is the height of the rocket?
I have the dimensions.
Just roughly.
I don't know. I want to say 10 something meters.
Okay, but so it's huge. I mean, 10 meters is like
it is. A lot. It is pretty huge. Yeah.
For 4 experiments, wow. Okay, that sounds.
Because and the thing is, there's 2. Actually, it must be bigger than that. There's 2 motors, right? Because there's the first, what they call boosters. There's the first booster, and once that one runs out, there's the second one that can bring it high enough. So it is pretty big. Yeah. Okay.
Where do you get these rockets from? So is there a company building these rockets, or?
As far as I know, they're mostly DLR. I know that I think the boosters Was it I think it's the boosters that are made in Brazil by a branch of the DLR.
Okay.
So,
Okay.
you know.
Okay, well, yeah, I guess if you send this rocket like in space, 200 or above 200 kilometers, has to be like huge power behind that. Okay, that sounds super awesome. So you are there like 2 weeks in advance and prepare everything and setting everything up, making the rocket and your experiment ready for takeoff. And what happens then? So someone presses the red button and then it launches. And what happens then?
Well, then we have a big TV screen in the room where we're all sitting with our computers, keeping an eye on our experiments, and we have this TV screen where Mars is actually, we have the inside of Mars there and what is going on there.
Like a video camera.
Yes.
Yeah. Okay.
So we can kind of follow it. The image isn't usually as good, but
Quite
and we just
shaky probably during the takeoff.
not really shaky, but more like there's problems in transmission sometimes, so
Okay,
that we get
okay.
some kind of weird colors and
Yeah.
stuff like that. But it's fine. And then it's just basically crossing your fingers and everything,
Yeah.
hoping that everything works in the next 6 minutes, and that's keeping an eye on whether you should stop the experiment if it's starting to go haywire,
Yeah.
something like that.
But you cannot really adjust your experiment once it's on its way to space.
It would take too long.
Too long.
We
Okay.
just don't have the time for it.
Okay. And when it comes down and it hopefully didn't crash into Earth but comes down
Or
smoothly.
fall into a lake. Which
or in a lake, yeah,
is
true.
also possible.
True, yeah. What happens if it lands in a lake?
Depending on the depth, it's either possibly recoverable in some time or it's just abandoned forever.
Oh, okay, so double risk, parachute failing or landing in a lake.
Yeah.
Is there like a risk calculation of what percentage is?
So because you have the test countdown first, where you kind of go through all the procedure, make sure everything is working well, and then you have the hot countdown, which is the actual true hot countdown, right? And just before that, you get a MET meeting, the meteorological meeting, where they show you the Swedish show you different graphs of wind speeds and directions of different layers of the atmosphere, and where they expect the rocket to land, and whether it's in our parameters or not.
Okay.
And that's usually how we decide when to do the hot countdown.
Okay, so if the wind current is like not so beneficial and might land with a high enough probability in a lake or something, then you just delay the hot countdown.
Yes.
And wait for better weather. I see. Okay, great. And then you recover your rocket. Who's going then? Or
usually there's one member of the science team that's kind of been told about all the others. Okay, what should you be careful of in case some experiment is damaged, and there might be some danger to the people picking the device up. So one member of the science team, 2 or 3 members of the rocket team, the what are they called, Morava team, and the Swedish. So fun fact though, last time I went along for the recovery, which was pretty awesome because we had to first go to a Sami village to talk with the Sami guys there, and we went by helicopter.
Oh, that sounds fun.
Yeah, that was the first
Nice.
part, really fun. Okay, and then they were like, okay, we can't go with the helicopters in the zone where the rocket landed because the reindeer are there and we don't want to bother them.
Yeah.
So they're like, okay, they pointed to this hill on the map, like, you go land here and we will come and get you with snowmobiles and take you to the rocket landing area. And so we did that. It's pretty amazing landscapes. Just wow.
I can imagine, yeah, great.
Yes, and so we landed there, and they had these 2 snowmobiles, and one of them pulled a wooden sleigh, like really, what you imagine as a really old-fashioned wooden sleigh with reindeer
really
fur on
traditional.
it, like, and we just had to sit on that while they drove us to the
That sounds.
the rocket land.
Super. Yeah, these are then the highlights of all the effort and the pain and the tears and sweat you put into your science. Then it pays off when you have something. That's cool.
So
that sounds awesome.
They managed to put the rocket on top of the sleigh, and so 2 guys rode back, like sitting on top of the rocket on the sleigh, pulled by a snowmobile.
That must be a hilarious
Yeah,
picture.
and I drove the snowmobile back. It was great. I
Oh,
mean,
nice.
come on. Yeah, it was really fun.
Awesome, sounds awesome. So, how big was the team actually? So, how many people are working together to get this rocket with all the 4 experiments up in the air into space?
The science team itself had, I think, 7 or 8 people, something like that. Less than 10 usually, and the Moraba, like, I don't know, 20 or something.
Okay.
Yeah.
So like 30, 35 people, something.
Yeah.
Okay. That sounds great. And then what happens then when you have you recover your experiment? Then you check the data, or what happens
Yes,
then?
you wait for it to warm up a bit because it spent some time in the
Yeah.
ice. Then yes, you recover all the data. You make copies from the of everything that happened to have a good quality stuff.
That's
Video.
for sure super. So every scientist who is listening right now, always back up your data like multiple times.
Yep. Yes, and then if everything worked as planned, then you don't really worry and you just start packing everything to leave. If it didn't work as planned, you want to know why, and so you start running tests again after the countdown to understand what happened and what to not do next time.
Okay.
Things like that, yeah.
Okay, and then you pack everything, then you come back to the institute, to Cologne, and of course the question, how was the experiment? So was it okay? Was everything running good so far?
Mars flew 3 times. The first time the plate got blocked while going under the powder container to get the new coat of powder. So that didn't work. I mean, we got a few layers. I think it was 2.5 or something, but there wasn't enough powder also on the plate afterwards. It didn't work. The second time worked pretty good. I think it worked actually ideally.
Yeah.
Only that you always have to be careful when adjusting the plate. That is what we need to work on at the moment, is making sure the plate doesn't have so much leeway or play in how it moves, because that in the lab it's not a problem because it's just resting, but in microgravity we notice on the videos that the plate kind of lifts at one side where it shouldn't, and that tends to then block or make the powder layer thinner on that side, so we had a slightly uneven sample the second time. The third time we had a completely different problem, which was due to us changing. We flashed the firmware, which means that we just put the default settings on again just to make sure that it was nothing weird happening. And actually, the default version on that was faulty, but we didn't know because the manufacturer just says, just flash it and it's fine.
Yeah.
But in this case, it meant that suddenly the laser movements were so slow that the laser didn't even turn on, and it took, I don't know, it was 10-20 times longer than it should have. So obviously on 6 minutes, that's a pretty problematic thing.
Yeah. I think all these flights, you learn so much, and you gain so much experience and knowledge about this new technology that, as we said earlier, there's of course there is enough room for improvement. Otherwise, it would not be science, or everyone could do it.
Every time you increase the length of your undocumented features list.
Undocumented features. We don't call it bugs here.
Yeah, no.
That's great. Speaking of new technology, I think the 3D printing process is not so new, but it's new that you perform this technology, or you apply this technology in space. So, is there any other group working on that as well?
This is quite fundamental. Because we worked together with the team to develop this powder, the gas flow powder system, so that it would hold the powder, right? That was developed together with people from the Bundesamt für Materialforschung.
Yeah.
They're now starting to want to make their own printer, but we still have the first one. Okay. And another team from China with whom we're also cooperating, they want to print with metals in space, but using filament printing and not the powder-based.
Okay, I see. Okay, so a slightly different
Yes.
technique. Maybe another question. What material are you using? I think you cannot use any material, so it has to be some kind of special alloy, or how do you
ideally
select
we
that?
want to make Mars work with anything, even
Yeah.
plastic.
Okay, yeah.
For now, my PhD is focusing more on metallic glasses.
Yeah.
So mostly metals are crystalline, but these ones are amorphous and they have cool properties. But because of this, they're also more sensitive to any temperature difference, cooling rates, and heating rates, which is quite an important part then in the printing process optimization. But we've also printed with this titanium aluminium vanadium, which is used very much in the industry in general, and so the printing process for that on Earth is very, let's say, known or secure, whatever you want to call it. But yeah, it's materials that are known for being good, possibly good tools, and we want obviously to have something useful for the astronauts, right?
Yeah, so the focus is really on printing like tools then in space.
Yeah.
Okay, yeah, makes total sense to have like known materials that work on Earth for this kind of 3D printing technique and then adapt it to space. Awesome. When is the first 3D metal printer in space on board the ISS? When is the first? Is there a 3D printer at the ISS right now?
They have a 3D printer, but for plastics,
for
right?
plastics.
For polymers, not for metals.
Okay, so it's probably not suited for printing real tools which you can work with.
Or they can do surprisingly cool stuff with it. But yeah, the problem for now, that this huge step that needs to be done before we can put it on the ISS, for example, is the powder handling. Because obviously on the ISS you cannot have the metal powder just floating around, because that's really toxic and dangerous. So part of the powder handling, kind of removing the powder from the part you've printed before being able to present kind of the part to the astronaut, right? But also recycling the powder, because the whole point is that we don't have to keep sending more tools or more powder. Instead, if we can reuse most of what is not used, which is the case in laser powder bed fusion, most of the powder isn't actually used for the printing. So if we can recover that, that would be great. But that obviously also implies being able to remove the partly melted particles as well, which would cause problems if you try to reprint with that. These might be preferentially from one metal within the alloy and not the others, so you might change the composition by doing that. So it's a pretty complicated part, that one, that we still have to work with.
What's an educated guess, you'd say? When is this ready for a first prototype somewhere at the ISS?
Part of me wants to say 10 years. Maybe that's too much, but it seems quite reasonable for me right now.
Okay. Is there anything you still want to add to the research project, or any very important aspect that we haven't covered so far?
Anything else? All right, a typical day on the during campaign, during the
when you're in Sweden.
Yeah, because with COVID it was made a bit trickier than usual, because you had the everyday COVID testing at 7 o'clock in the morning.
Okay.
And then you waited for the result, 15 minutes, and then had breakfast, and then worked until, for us, last time, because we were missing one colleague because he got infected just before leaving, we had to work not double, but we worked until 10 or 11 p.m. for the first few days, from 7 to 11 p.m. That was quite intense. For like 14, 15, 16 days? Yeah, it wasn't the whole time, luckily, but during campaign we don't have weekends, right? Just after about, 8 days, it's like, okay, we can get a day off. So it's pretty intense, that was. But it's also a great opportunity to really spend some time with your colleagues and really get to know them. When you know them in really difficult situations, it's kind of testing the person to the extreme, and you see what comes out.
Exactly. So. This is so true. It's like if you go with your friends the first time on a vacation, and then you're spending so much time on very little space with each other.
Exactly.
And this is like a scientific vacation. Of course, it's super hard work, but I think it's also fun if you are able to go to Sweden and to work on a rocket and launch a rocket.
Well, the first time we weren't, because of Corona, we weren't even allowed to leave the place to go anywhere.
Oh,
So we
okay.
could walk within the base, basically, and the ground of the base. But
I think that's it for today. Thank you very, very much for joining me on this very first episode.
Well, that's it for today. If you have any questions to Mélanie or me, feel free to reach out. You find me either on Twitter or LinkedIn. The best thing really about this podcast is that it's about you and everyone can participate. So if you want to share an exciting story about your science, your academic life, some crazy experiments or any other nerdy stuff, feel free to drop me a short message. Thanks for tuning in, take care and see you soon on the next episode of Your Friendly Physicist and Other Nerds.